1. Oh, almost there. Okay, and we are live. Alright, I am Wyatt Wismer, and I am here with Michael.
Hello?
And I may have broken my OBS.
I'm frozen.
Yeah, let me
To myself.
unfreeze Michael real quick. There we go. Now we can see Michael in real time. Yeah, so today we are doing our contest walkthrough workshop. So I guess this is aimed to be preparation for the ICPC tryouts, which are coming up on February 13th. So the plan for today is we want to walk you through some questions, and we'll really walk through all of the question, from first reading it to I guess actually interpreting it, what it's saying, and how you might go about solving it. So I guess if you want to try these questions yourself, I think Michael might post the link in the chat or something. You can see
Yes.
this is last year's contest, and you guys can if you visit this link and press sign up, I think you can go and write these questions if you didn't write them last year. So to any first timers, this site is called HackerRank. You may have used it before if you've ever done a take-home HackerRank interview, or if you've ever tried one of the HackerRank contests. So typically a HackerRank contest will have a few questions. Like you see here, we have these 6 questions, and typically they start easier and they tend to get harder as you go on. And similarly, you get a certain number of points for solving a question, and you tend to get more points as they get harder. And I guess one other really big thing to point out, and this is a difference between HackerRank and ICPC, is that in ICPC, every question is all or nothing. So you either get full points for a question, or you'd get no points for a question. However, HackerRank's kind of fun in that if you only have a half-baked solution, something that maybe is a bit too slow, or maybe you fail in a few edge cases, you can still get partial points. So even if you don't have the perfect solution, you should still try and implement. I guess so. With all that in mind, let's dive into the first question. So this question's pretty easy. It's called 789, and I guess I'll read it through real quick. So it has a bit of flavor text. I'll try and read through this quickly, I guess. So why was 6 afraid of 7? Because 7, 8, 9. So okay, 6 wasn't only afraid of 7. Though it turns out a lot of numbers are hungry and have started eating each other. Can you figure out which numbers survive the feast? So let's keep reading. Alright, so you're given an array of numbers. Each number is either 8 or an integer representing a feast attendee. Consider 3 adjacent numbers in the array, A, B, C. If B equals 8, then A, 8C during the feast. So if the array was 6, 7, 8, 9, then 7, 8, 9, and the survivors are just 6 and 7. So it looks like what they're saying here is that they're going to give us an array of numbers, and if the number isn't 8, then that number just represents someone who's attending the feast. But if we ever have a number, the number 8, and then another number, that means that the number after 8, I guess, gets eaten and removed. And so let's keep reading. It says, the following is guaranteed. The only duplicated number in the array is the number 8. Okay, so all the other numbers are unique. Excuse me. All 8s are separated by at least 2 numbers that are not 8. Okay, that's really useful. That means we can't have 2 8s in a row or something, which seems it would be kind of ambiguous. I wouldn't know what that would be. And they say it can't start or end with an 8, which is also good, because then it's sort of also ambiguous. What do you do if there's 8 at the end? Do you eat the start or something strange? So we don't have to worry about any of that, which is nice. And now, so let's look at the input format. So our first line is going to be an integer n, and the next line is just going to be n space-separated integers. And it looks like we just have to simulate the feast, which is to say we simulate the 8s removing the next element. So I guess the first thing to do is to take input here. So let's do that real quick. You'll see I'm using Python. Today we're going to be using a mix of Python and C++. But I find for short little questions like this, Python can be really nice, because you can pop something out in 2 or 3 lines. So let's go read in the size of our array, which is n. And then we can read in our array. This is my favorite trick. I talk about this trick every single time I do a stream. This always gives you an array in Python. The idea is input gives us a line, input.split gives us a space-separated list of strings. When we map it to when you call map int, that's effectively calling int on each element of your array. And because we're in Python 3, that actually returns like the really weird like generator type. So we have to cast it to a list at the end of the day to get something that we like. So now that we have all that, I think my approach is going to be, I guess, pretty simple. I'm going to iterate through my array. And if I see a number that's not 8, I'm going to print it out. And if I see a number that's 8, I'm going to skip ahead 2, so I skip the next number. So let's try coding something like that. So I guess if I want to iterate through my array, I could keep a variable to show where I am in the array. So let's call that I. So I'll iterate through. And I guess what I said was, if 8i isn't equal to 8, then I can just print... or sorry, I say print. Actually, we could... No, that's too silly. Well, I think the easiest way to keep track of our answer is just to have another array. So I'll make another array called res, which is sort for result. And I'll just stick my answer there. So I'll say res dot append... What is this? Sorry, append 8i. And then we move on to the next element in this case. Now our other case is when we have an 8, and we don't have to print anything for 8. I guess all we have to do is like skip 2 ahead. So here I can just do I plus equals 2. And then I'm going to use another sneaky Python one-liner. So right now our result contains a list of integers. And I'd like to print those out to the screen. So if I did map string of result, my list of integers would become a list of strings. Although I guess technically not a list. It would become technically a generator of strings, but you don't really need to worry about that. And then there's a thing in Python called join. You can go like a string thing dot join, and it will join your strings with whatever symbol you put here. So if I put like a colon here, for example, it'll put a colon between every number. See, I want to print my things space separated, so I'll put a space in my dot join here. And if I print all that out, I should just print out my answer. So let's try that and see how it goes. Okay, so we pass the sample inputs. So if you guys haven't seen too much HackerRank stuff before, so HackerRank normally gives you a few sample inputs you can test your code against down here. So you can see like what the input is, what the expected output should be, and what your output was. But there's also a bunch of hidden test cases which you can't see during the contest. And when you press submit code, it goes and it runs against those hidden test cases. So here we see we've passed all the test cases, so we got full points, which is good.
Nice.
So I'm going to go back to the screen, and I'm actually going to switch over to Michael, and he's going to walk us through problem 3 from last year, which was Technet. I think, Michael, are you the author for this question too? I forget.
I am the author, yes.
Okay,
and you can tell based on the algorithm used to solve it.
Sorry, let me make sure you're actually here. I have to do this. There we go. Okay. You are all set up.
All right, you can see everything? I'm scrolling?
Yep.
All right. Okay, so this is Technet. It is question 3 from last year. So this one was a medium question. So the general problem is you're working for some company called Hypercorp, and you're an intern there. And your job is to solve a problem that they have. So right now they have all these servers, and they're hooked up with these cables. And each cable has a certain length to it, right? So from server 1 to server 2, you have a length of 12. From server 1 to server 4, you have a length of 15. Your goal as an intern is to minimize the amount of cable used and also connect all the servers together, right? So what are some optimizations we can do here? So this is the initial server setup. So this one could be optimized. So right here we have server 4 connecting to server 3, and that's using a weight of 37. But we can get rid of this to 37 and use this cable of length 2 instead. Right? So that makes sense.
Yeah.
And then
just to clarify too, just like to talk through like the problem flavor. So wait, so it's like every server has to be connected to every other server, I guess?
Yeah.
Okay.
So a server is connected to the network if it has one connection at least. So you just have to have at least one connection. You can have more than one. It'll still be valid, but our goal is to like minimize it. So we wouldn't want more than one connection.
Okay.
Yeah, so example here, like in this setup, they have 4 is connected to server 1 and server 3. But server 4 only needs to be connected to one of the servers, right? So we can get rid of this guy.
Yeah.
And everything will still be connected. All right. So the first thing I like to do when solving problems is just to figure out what the input is and then work from there. So scrolling down, I look at this input format, and I see on the first line we have 3 variables, S, N, and M. So I'm just gonna start, oh, spoilers. You guys can S, N, and M is equal to, I'm gonna do White's trick here. I'm gonna do map int input dot split. And then what else is next? So we know that we're going to iterate through n lines and read some inputs, and then iterate through m lines and read some inputs. So let's do that. So for blank in range n, we're going to do some inputs.
But what are we inputting in? Sorry, I totally forget.
It's
like the first one.
So we're going to get. Oh, sorry. Yeah, I should have went over that. So in the first line, we have 3 variables. We have S for servers, N for the existing configuration, and then M is for potential connections, right? So if we look at this diagram, N would be these bold lines. So that's what our current network setup is. And then M would be all these dotted lines that aren't in our network, but we can add them, right? So for this question, we're allowed to remove from our existing and replace it with something here. But we don't have to replace it. We can just remove it completely as well if it's not needed.
So we can use like any combination of any of those, I guess, then?
Yeah.
Wait, I guess one insight then, does the initial configuration matter then at all?
Yes, it does, because our output has to be the difference. So we have to, so it's at the end of the internship, and you got to say how well you did. So you got to provide some numbers, right? So you gotta give the numbers.
Get on the stage.
Yeah, you gotta put some numbers out there. How much wire you saved? So you have to account for this initial position. So the second thing, so we're gonna have M lines here. So for blah in range M, right? We're gonna get some more inputs. So let's process the first guy. So this is our current configuration, right? So as Wyatt mentioned, like the only important thing about keeping track of this is knowing how much wire you're using initially. So I'm just gonna add a variable called old setup, and that's gonna be an integer, and that's just gonna add up how much wire we're currently using. So let's do that. So x, y, l input dot split. And then we're going to do old setup plus equal L. So that's going to add it. And then we're also going to have to add this connection into the list, into some list, because we might have to use it later for the optimization. So I'm going to make a new list called connections, and I'm just going to append that.
Are you just going to store it as like an actual, just a list of edges, sort of?
Yeah. I'm just going to do like a tuple, x, y, and its distance L.
Nice.
Yeah. And then for the second for loop, we're just iterating over our potential connections. So we want to add that to our connection list so that we can process it. So let's do connections, append, and then we need, it's basically the same thing here, right? So we're going to append that, and now we have our connections, and now we can optimize this setup.
Cool.
All right, so the algorithm I'm going to use is something called Kershaws.
So what Kershaws is? I don't even know the pronouncing.
I don't know how to spell it.
I always thought it was Kershaws, but I sort of feel like I'm butchering it. I don't know.
No, I feel like that's right.
Is it? I don't quote me on that. Our viewers can like look it up.
Yeah.
I don't know.
But that's what I'm going to use to solve this problem. So Kershaws is, or Kershaws, I don't know how to pronounce it, but the algorithm is used to generate something called a minimum spanning tree. So how we can look at this network is we can look at it as a graph of nodes and edges, right? And the whole idea with the minimum spanning tree is what is the minimum length or like edge
I guess
Edge
like
length
the minimum
sum.
like sum of edges, yeah, that you can reach.
Yeah, the minimum sum of edges that connects all these nodes, right? So I know there's Prim and Kershaws. Is there any other algorithms, Wyatt?
Those are the ones that I know of or have heard of for this.
Yes. I'm going to be using Kershaws because it uses union find. Does Prim use union find?
No, Prim's you implement like a lot like Dijkstra's. It's like very similar to Dijkstra's.
Okay. So union find's like my favorite algorithm. So I will be using Kershaws. So let's set up union find. So
wait, before I jump into union find too, I'm gonna be a tough audience.
Yeah. Go ahead.
I was gonna say, how do we know that? I'm sort of curious. How do we know that like our sort of like minimum spanning set of edges is a tree and not like a different graph or something? How do we know that it's a tree? I guess.
Ooh, Wyatt. You learned this in algorithms.
Sure, I did learn this in algorithms.
What was it? Wait, did we do that in second year?
Yeah. This is an easy question. The hard questions after.
Yeah. Okay, so.
Like, how do I know that doesn't have cycles? I guess.
Yeah, the reason it's a tree is because our goal in the minimums, or like to minimize the number of edge connections, is. Oh, sorry. So we want to connect all the nodes, right?
Yeah.
And if we have two edges, I guess that means that we have an unnecessary edge because one node is already connected.
What do you mean when you say you have two edges? You mean you have a cycle? Or?
Okay, sorry. So let's look at this network here.
That'll be cool.
Right? Okay. You have everything's connected, and we have this cycle here, right? So the goal of minimum spanning tree is to connect everything and minimize the length. But if we have this cycle, that means that some node is added more than once.
Sure.
I don't know. Why? You gotta explain it.
I'll give you the mini proof. This one's actually really easy to prove. So all right. So this one's just like a proof by. Yeah, it's really just a proof by contradiction, I guess. So let's say the best answer did have a cycle, right?
Yeah.
Then we could take that. Answer, take any edge that's part of the cycle, remove it. We would still have a spanning tree, and we'd have a better answer. So therefore, the best answer can't have a cycle.
Makes sense. Yeah. Yes, makes sense. You explain it so well.
Well, thank you.
All right, so union find.
Okay.
Also, if you guys have questions, I have the chat open, so feel free to ask something in the chat or comment about anything. Okay, where are we? Okay, so union find. We have a very common setup, so I like to just create a parent array.
Oh, what is union find too?
Right.
I'm like.
Oh, union find.
No, it's been a while,
so union find.
I actually honestly haven't implemented union find in so long.
So union find is used to determine if two nodes are connected. It's a really fast way to see that. So normally, if we have the setup, right? If we want to know if, I don't know, let's say server 1 is connected to server 3, right? The way we check that is we have to traverse to server 3 from server 1 and see if it's in the same, or if it's connected. So in this case, we go like server 1 to like server 2, then there's like no edge there, or then we go back to server 1, then go back to server 1 to server 4 to server 3, and then like, okay, it's connected, then it goes back. But because if you look at our like test cases, right, we're gonna have a lot of servers. So if we keep doing that traversal, it's gonna get really slow. So union find is a fast way of determining if two nodes are connected to each other.
Yeah.
If that makes sense.
I guess it's like, how do you even describe it? It's like, like with union find, you almost like say I've got n things, and then there's an operation to say like take thing like I and thing j, and they're connected now.
Yeah.
And then like
so it's kind of like you're adding them to like the same group. So you'd be like, is server 5 and server 6 in the same group? Is how I like to look at it. So the initial setup for union find is for I in range S. So the initial setup for union find, every server is not connected to anything. So everything is like on an island until we add edges, right? So server 1 is in group 1, server 2 is in group 2. And then if we add this edge here, server 2 will join server 1's group. So now server 2 is part of group 1, right? And just to keep the array math simple, I did this by 1 index. So I'm just going to do -1 on everything, just to 0 index everything. Yep. So for find, the way we determine if something, so find, what this does is it says what group am I in, right? So if x does not equal the parent of x, parent of x is equal to find parent of x, and then we return parent of x, right? So this is, we say something is, so let's say server 1, right? Server 1, so initially, server 1 is in group 1. So if we look at this parent array, we'll say 1 does not equal to parent of 1, which is false, so we'll just return it. But later on, when we connect something, we'll say 2 is in group 1, so 2 will have to traverse up one step to see if it's group number. Yeah.
Also, if you're in the comments and like any of this is like weird, like, well, this feels familiar because we've coded union find like 100 times. Like, stop us like any problem.
Yeah, that was a horrible explanation, but you know.
Actually, what do you even do? I think we
play around with it.
Actually, wait. Finish coding like union, and then I think we could do like a Jamboard or something just to like draw it, because I feel like it's super intuitive once you see it.
Yeah. It's kind of hard to explain without.
Yeah, so like bear with us. It's gonna might seem like weird now, but it will make sense. And if it doesn't make sense,
so
ask us in the chat.
Yeah, so for union, I'll make 2 variables. So I'm gonna do x group. So what group does? Okay, I'm gonna rename this to group, just so it's easier to explain later on. Is that fine, Wyatt?
Oh, is it really group? It's more like, because it doesn't necessarily say the group. Like it just says your parent, right? Like your parent might not.
Yeah. Okay. So x, the parent of x is equal to find x, and then the parent of y is equal to find y, right?
Yeah.
And then if their parents are the same, that means we're combining 2 groups together. Oh, Tommy said we did union find last week.
Oh, perfect.
Wait, in class.
You can compare us to Kershaws then. Please roast Kershaws for me.
Compare our algorithm.
If ours is worse though, like don't tell Kershaws. Kershaws will roast me instead.
Okay, don't worry, Tommy. We'll plan to see you way better.
Yeah.
So if x does not equal y, right, that means they're in different groups, so you want to merge their groups together, right? So to do that, all you do is you point one of the parents to the other parent, right? So it doesn't really matter which one. So we'll do parents at x parent is now equal to y parent. So we're saying x's parent is now, so y is now the parent of x's parent. So we'll draw that out. If it doesn't make sense. Okay, and that's union find?
Yeah, that's the whole code. It's super clean to implement, eh? Wait, what should we do? I guess we can do the code gen now.
Let's go jump over before I add more logic, because this is like the basics for union find, and then we'll add the logic to this to solve the problem. Wyatt, you can explain it because you're so much better explaining them.
So I love explaining union find.
Yeah, you can explain it.
Okay, wait. Can you open up the? Oh, wait, I don't know how I expect you to open this up. I haven't sent you the link. Let me do that.
Jamboard.
You
want to make the jam?
I already made one. Even I just didn't send it.
Yes.
Okay.
Send it on Facebook.
On Facebook. Okay. Wait. Wait.
I'll send it on anything. Whatever's easier.
I'm gonna send it to you on Meet.
Okay.
Here's the chat. Okay. Bless.
I have it open. You can see it, right?
Gorgeous. I see it. It looks lovely.
Okay.
Cool. Let me just shift this over a bit. Perfect. Okay. Alrighty. So union find. Fun algo. Wait, let me see. Is this weird? Oh, okay. That makes sense. I saw your mouse, Michael, and I thought it was my mouse, and I was like, they were offset. I was very confused, but it's okay.
No, you're good.
Okay.
I'll hide my mouse.
Yes. Ooh, no, it's fine. Okay. So I guess as we mentioned earlier, union find is useful when we start off with a lot of things that are all sort of like separate, and we want to support an operation to like clump 2 things together. And I want to be able to tell like if 2 things are in like the same group or same clump or same whatever you want to call it. So this will make a lot of sense when we draw it out. So let's say first I've got some dots, which I'm gonna name. Here, I'll go. Oh, these dots are very small. Okay, wait. This. Let's do this. Yeah. Oh, that looks nice.
Oh no.
This one. I just want a big guy.
I think Jamboard's really laggy. Like everything comes out very.
Okay, how well can you see that? Oh, pretty well actually. I'm gonna use that. Okay, sorry. Forgive us for this.
I'll just zoom in.
Yes. Ooh. Okay, beautiful. So
Okay.
I'm gonna make some dots.
Oh, where my
Some beautiful
my
dots. Let's make this guy a bit nicer. Okay. And now I'm gonna number these dots. So let's say I've got some dots numbered like 0, 1, 2, 3, and so on.
Can you see me editing?
Mm-hmm. Oh, cleaning up my dots. Thank you.
I'll clean these up for you.
Okay, so I guess the idea with union find is to start, we've got like all these dots, and we can think of these dots as being in their own group. So they're all like completely separate and like unrelated to each other. But then we want to support like a union operation. And what that would do is it would take two dots and put them in the same group. And how we do that is like, let's say we want to do like, I'll say UN for union, and let's say I'm calling union on 2 and 3. What I would do is I would look at node 2. And right now, I'm already at the top of my tree, which doesn't make any sense yet, because it's only one node, so I guess of course it's the top of its tree. You'll see why I say tree later. So I've got this node. And I've also got this node 3. And all I'm going to do is take take one of my nodes and point it towards the other one. And now, why is this useful? Now I can see. So actually, I guess we can't see the code as well. But we defined this operation called find, and all find does is follow these arrows coming out of each dot. So if I call find on a 2, for example, it just gives me 2 because there's no arrows I can take. But if I call find on 3, then I follow this arrow and it takes me to 2. So then what I can do is if I call find on 2 things, like if I do find on x, and if that's equal to find on y, then my 2 things are in the same group. So
it's kind of more like, is it kind of more like the arrows are pointing to itself? So like the path ends?
Yeah, actually, sorry, we should even draw that, yeah. So to start, everything's pointing at itself. And if something's pointing at itself, that's how we know we're at the top of the tree. But then, whenever we merge things together, instead of pointing it at itself, we have it point at something else.
Yeah.
Yeah,
so you keep traveling. So let's do like 6 to 7, then 6 to 5. So you kind of go up that path.
Good idea. Okay, so let's say we do 6, 7. So we arbitrarily take one of 6 or 7 and point it towards the other. So I'll take 6 this time for fun, and I'll point it towards 7. Okay, so now here we would say that 2 and 3 are in the same group, and that 6 and 7 are in the same group. But now the really funky thing we can do is let's make it really weird. Let's do 6 and 3. Okay?
My gosh.
This one's kind of nasty, but if you understand this one, you'll understand the full thing. So you'll notice here that 6 is not the top of my tree. So if I want to run union on 6, 3, so actually, yeah, sorry. I'm going to go through the like pseudocode for union here, like based on what Michael wrote. So in Michael's code, we had like union of like x, y, right? And our first step was we did like parent of x. We wanted to find like x parent and y parent. So here, like our x parent is the top of the tree that x is in. You can call it like an identifier for the group or something. So let's say I'm looking at 6. If I follow my arrows all the way up, which is what our find function does, it would bring me to 7. So my x parent here is 7. Now for y parent, I actually do the same thing. So I'm going to look at 3 and say, alright, 3, is he at the top? Nope, he has like an arrow coming out of him. So he goes to 2. And now 2, I can't go anywhere, I'm stuck here. So this is the top of this tree. So that means my parent for 3 must be 2. So these are like I guess you could call them the roots of our 2 trees that we want to merge. And I just say the parent of like one of these guys equals the other. So I could say like parent of like x parent, let's do Yeah, parent of x par equals y par. And so this is equivalent.
Yeah, that's what I did.
Yeah, this is equivalent to doing, so x par here is the 7. So this arrow that was pointing to itself now becomes an arrow that points to the root of this tree, which is 2. So now you'll see if I choose any two numbers, like let's say I chose like 3 and like 7, but if I choose any two numbers that are part of this group, then when I follow these arrows, they'll bring me right to the top, and I'll see them in the same group. So for example, if I choose 3 and 7, like from 3 I'd walk all the way up to 2, and I'm at the top here, so I'd stop. If I'm at 7, I'd walk from 7 to 2 again, and I'd stop because I can't go anywhere from here, and I'd see, oh, I'm in the same group, so I must be connected. So this seems cool.
Yep.
It seems like it would give correct results, but the hard thing is like proving the runtime. Now, I won't really formally prove the runtime here at all. If you're interested in the proof, and especially if you're in second-year algorithms right now, the red like Cedric textbook that you use has like a really good proof for the runtime. Just doing this will give you like runtime that's like logarithmic. If you do this, plus you do something like keeping track of either like the sizes or the heights of these groups, you can actually get the runtime down to like almost constant. It's like, I think technically it's like this really weird thing called the inverse Ackermann the inverse Ackermann function or something. But that's not something you'd ever need to know. It's just like it's like so it grows so slowly it's effectively constant. So it's a super fast algo. So we don't even need that. We're like fine with logarithmic runtime. So we're gonna stick with that.
Mm-hmm.
Does that make sense, Michael? I don't know.
Yeah, that made sense. That was good. One thing I added was path compression. Path compression is this little trick you can do to really speed things up. So let's say we do this like query of like find. So we want to find 6 a lot.
Yeah.
So what path? Oh, let me change the color. Oh, it's too late. So if I want to find 6 a lot, right? I have to go down this entire chain of like 6, then 7, then 2, then 6, then 7, then 2, 6, then 7, then 2. But because I already know the answer is 2, what path compression does is it will automatically, when you call find, it will point to 2 on the way back down.
Yeah.
So it'll call 7, and 7 points to 2 already. Then 7 comes back, and then 7 returns 2 to 6, and then 6 will automatically point to 2. So the next time you call it, it just jumps straight to 2.
Yeah, I guess I could say, actually, I like Michael's explanation, but it's like, if I call find on a node, I walk all the way up to the roots, and then when I'm going back down in my recursion, I set every node to point to the root. So that next time, if I call anything that was on that path, I can just jump directly to the root, which is super handy.
Yeah, and that's this one line right here. So just this one line here.
Yeah.
Inverse Ackermann. Wouldn't that be? Oh, Tommy asked the question.
Oh wait, he's gonna call me out for. It is literally almost a 1. I think. Yeah, you could probably look up the actual number. I don't think it goes past 4 for like something ridiculous. Like I think you can go into like the 10 to the something obscene, and it's still less than 4.
All right. Should I continue the question? All right. So, okay. So after you have this set up, what you can do now is implement Kershaws algorithm. So with Kershaws, I think the assumption you make, it's not an assumption, it's a proof that like, if you just join based on the shortest edges, you will have a minimum spanning tree. Is that correct, Wyatt?
Yeah, it's like you can greedily always take the smallest edge. And you're guaranteed to get an MST. And I guess if you want the proof of this proof is also in your red Cedric textbook, and it's very well explained. It's like another like proof by contradiction. Yeah, sorry.
So to do that, I'm gonna do. I'm just gonna iterate through that. Sorry, my bad. Okay, I'm gonna iterate through this list of connections that I made, but I'm gonna sort it. So for let's say for edge in sorted connections, and you want to sort it based on the length. So I'm just gonna add a key here. Key is equal to lambda. So this key is just a custom comparator, lambda e, and I want to do it based off. Oh, what this key does is I want to take some edge and I want to compare it based on the second index. So the second index would be L. Right? So that's how that's doing. Am I missing? Okay, no.
Yeah, this parentheses good.
Okay,
They look
for
good.
edge, it's sorted. Oh, Lucas is here.
Oh.
For edge and
Yeah.
sorted, we're gonna do union on edge at 0, edge at 1, and then edge at 2. So I'm gonna pass in all this data into this union function. So I'm gonna attempt to connect it, and then what is this? Give it its length, so I'll know how much to add it by if I do connect it. So the next thing I need is I need a variable to store the new setup, the length of the new setup. So I'll just make that here, new setup.
Wait, Michael.
So it's gonna,
I'm so confused.
Yep.
Why does union take in 3 things?
Oh, it's just to speed things up.
What?
I'm just gonna do. I'll show you. Don't worry.
You show me some big
it'll-
brain. Or do you add it to or something during union?
Yeah. So like,
okay.
yeah. So during union, if we make that group, right, we can just do a new setup plus equal L. That's all.
Oh, okay, yeah. Normally you wouldn't have that. Normally your union would only take in 2 arguments, but Michael's like hyper efficient.
Yeah. So normally union's like this, but I did it like this. Oh, not like that. Like this.
I guess it's like when you merge things together, you pay the cost to merge them together. That's really clean. Actually, that's cool.
Yeah. And then all you have to do is just print out the output. So you just subtract the old setup minus the new setup. Like that. And you run the code. Crashes, of course, for I in range S. What was that?
Oh wait, that doesn't make sense. What do you want to? You need to be like some value for I in range S, like probably. I for I in range S. Yeah. So I guess you remember in our diagram we had every arrow pointing to itself. So at the start we have to initialize our parent array, so everything has a reference to its own like indice, like a pointer to itself effectively.
Input.split.
Oh,
I forgot.
Tommy has a question in the chat. Is the union merging 3 nodes? No.
No, it's not. It's merging 2 nodes.
Yeah.
So I'll put a comment here. X is equal to node 1, and then Y is equal to node Y. And then L is just the length between node X and Y.
Yeah, so I guess it's merging nodes X and Y, and it's just like adding the cost of like L
Yeah.
to our
So
to our like,
you can see that.
for some reason.
Yeah. Add L when connecting to a network. There you go. Oh, that's lowercase l. And then let's run it. Parents not defined. Oh my gosh. Parents.
Also,
Parents.
I got something beautiful for the stream. Here.
What is that? Oh.
Here. This is what you need.
Put that beside me as I do this question.
Here you go.
Parents not defined. Oh my gosh.
Michael's book.
Parents. Am I parent?
What do you have a bug? Wait, let's see.
Oh, parents. No, I called it parent, and there you go.
Oh, that'll do it.
Submit it. Go. Yay, I got it.
Hey, nice. AC. Easy peasy.
All right.
Oh, now I got a fun one.
All right, this is the hard one now. This is the really challenging one. So, so this is this on me?
So yeah, let me turn off. I gotta keep my Sedgwick book, of course. Here, I'll move the Sedgwick book up to me now.
Okay.
I'll need it. And here, baby Sedgwick. Here we go.
Yeah.
And I'll turn off Michael's thing. Here we go.
Yeah. So this, for the trials last year, Wyatt was the only one that was able to solve this.
I think it was also, so you'll see today I'm going to be doing this in C++. I think you actually can't get full AC in Python, which is unfortunate.
I'm going to send the problem chat for people who want to do it while we're doing it.
Actually, I really love this problem. It's a really, I don't know, it's almost like it's like a standard sort of DP problem with a twist. Twist, it's cool. Okay.
Oh no.
So, I guess even before I dive into this, I should like sort of preface all this. So this next problem is going to use a technique called dynamic programming. So that's probably like by far like the scariest sounding programming technique. But I don't know. Effectively, most of the time, if you're doing dynamic programming, it's just like you're writing a brute force solution, and then you're like almost like caching your results. Like there's I'm technically not like totally being correct when I say that because there's like bottom up ways, but even that those are kind of similar. So yeah, so dynamic programming it's not super scary. It's effectively like recursion with like caching. That's like what it really boils down to. And so we're gonna go through a problem where we do exactly that. We're gonna write a brute force solution first, and then we're gonna explore how we can like store our answers and why that's fast. All right. Oh, Lucas got a wrong answer. Not even a TLE.
Yeah, I got 8 points for this for just doing print 0.
Was that? Hopefully, the contest will be less susceptible to that this year. In the past, when the authors are less experienced, you can often get a lot of points just by printing out like cheese solutions, like printing like 1 or 0, or like some other simple thing. So always keep that in mind. Okay.
I feel like mine had a lot of print zeros.
Yeah. I remember a while back. Oh, I'm going on a tangent. But a while back, there was the IEEE Extreme contest or something. No, not even the Extreme. It was like the IEEE
Oh yeah.
T-shirt one. I don't know, but we got like hundreds of points by just printing
Oh yeah.
zero
We,
or like.
we used Sophia.
Yeah.
She was grinding it. She was working so hard to solve every problem, which is like printing zeros, printing ones.
3 points. It's a good time. Actually, I guess my friend was the organizer for that. He's probably trying out for ICPC this year. So I hope he's listening. If you're listening, I'm waiting for you. Okay. So sorry, we went super off topic, but I'll dive into the question now. Okay. So this problem is called a white space strip. I don't know who wrote it. I feel like Mikhail had to write it. But let's dive into it. So white space is a programming language where only space, tab, and line feed characters have meaning. It actually is a real programming language. Surprisingly, it's pretty gross. That's all. To celebrate this glorious language, the CEO of Whitespace asked you to design a keyboard called the Whitespace Strip. So it's a miniature keyboard that is optimized for writing whitespace code. So it only contains a single row of either tab keys, return keys, or space keys. And respectively, these will occupy only like one spot, like 1 unit of space, 2 units of space, or 3 units of space. So that's like tabs are 1 unit, returns are 2 units, spaces are 3 units. And I guess you can see that already in the diagram down here. And so we want to find out the total number of layouts that we can have such that we exactly fill up the n units. And here's what makes this problem hard, such that we have at least one tab character, return character, and space character. Fun. Okay. And that's actually the entire question. So it's pretty simple. So there's no way I'm going to jump straight into the code for this because it's pretty confusing. So I think I'm going to go back to our Jamboard. I guess, Michael, could you go back to the Jamboard? This section might be easiest. I'll just go through you.
Yeah.
All right, beautiful.
On page 2.
Page 2, beautiful. Okay. Okay, so let's quickly go over what we know. So we know we've got some region of size n. It's like n spots that we need to fill up. And I've got like a tab character, which fills up 1 spot. I've got a return character, which fills up 2 spots. And am I doing this right? Tab return and space is 3, right? Yeah, okay. And I've got a space character, which I should probably draw it bigger. I've got a space character, which fills up 3 spots.
Okay.
And so I want to figure out the number of ways that I could fill in all n of these spaces, so with no holes or anything, using just these like 3 pieces. And such that I have at least one of them. So I guess a simpler version of this problem would be if we don't worry about having one of everything. We just say like, how many ways can I fill up this space using things of size 1, 2, or 3? So let's think about what that would look like. I guess we could solve that with like a recurrence. Sorry, like recursion. We could say something like, well, what? Let's say that we have some function f, and let's say that f at n is like the number of ways to fill in. Like the number of ways to fill in like one of these things of size n. So I'll say like number of ways to fill in size n. So then, I guess we could do like, well, f at 0. There's exactly one way to fill in something of size 0. And then, I guess we could go through this manually if we made like a little chart or something. I could go like, what? N and f of n. So go through like, so well, 0, there's one way. Well, let's say n is 1. So n is 1 corresponds to having like a single space that I need to fill in. So I could only fill that in with a tab. So I guess there's one way of doing that. N equals 2. Sorry, n equals 2, I could fill it in with like 2 tabs, or I could fill it in with a return. So that'd be like 2 ways. N equals 3. We think like, oh, now it's a lot trickier, because now it's like, I could do a space, I could do tab return, I could do return tab, or I could do tab tab tab. I think that is 4, if I did my numbers right. Okay. And now, we'd really like to find a pattern here for this. And so let's think, well, like, let's say I'm dealing with an arbitrary thing of size n, right? And I think, well, I've got 3 options normally. I can always place a tab thing, a return thing, or a space thing. And, well, these things are of size 1, 2, and 3. So, I guess the number of ways I can fill in something of size n if I choose a tab here is just equal to f at n minus 1. So that's to say, if I've got n things, and I place a tab at the start, then the number of ways that I can have this configuration, like work, I guess, is just f at n minus 1. So it's the number of ways I can fill in the remaining space. So similarly, if I did like a, let's say I put in a return thing at the start, then the number of ways I can have that configuration work would be like f at n minus 2. So that's to say, I fill in the first 2 spots with a return thing, and the number of ways is just the number of ways, once again, that I can fill in the remaining space. And we can do the exact same thing with return. So if n was large enough, so I guess specifically I should say, if n is greater than or equal to 3, then this would be the number of ways, like f at n would equal this. This would be the number of ways to get this. So that seems like pretty easy, I guess. That seems nice. So then if you're solving this, let's move to page 3, Michael. We could do, yeah.
All right, there you go.
Normally, in terms of actually implementing that, we'd make like a DP or something. So normally to do a DP, you just allocate like an array or something. Like I'd allocate an array of size n. And I'd say that like DP at n is like the number of ways to fill in size n. And then I could just like solve this recursively to say like, oh, I basically just like, I just do this recurrence. Like the number of ways I can do this is the sum of the number of ways I can do it by doing space, by doing tab, plus the number of ways I can do it doing space, plus, that's fine actually, plus the number of ways I can do it doing return. So you just sum up all of the different ways. So that's pretty easy. What's harder is keeping track of this whole idea of I have to use a tab, I have to use a space, and I have to use a return. So how we could do that, like this is really like the big insight in the problem, if you can figure this out, you're like good, is let's add a few more things to our DP. So instead of just DP of n, let's have DP of n t, what do I say? Tab return space, sorry, TRS. So here's my idea. So this variable n, right, it can go, I think we can have up to about 10 to the 5 things. So it can be at most like around 10 to the 5. But let's make like 3 more things we index by, and let's make these like super small. Let's make these like only of size like 2. And the idea is, so this is almost like a flag. So if it's 0, that would represent we don't have a tab, and if it's 1, that represents we have a tab. So what I'm saying then is we can use these 3 variables, or sorry, I guess like these 3 indices, to indicate whether or not a certain state has a tab. Or sorry, a tab space or return. So I guess
so store 0 and 1?
Yes.
Or it'll be like index 0, index 1.
It's exactly that.
Okay.
So these will be 0 or 1. So then,
Okay.
sorry, this whole state thing might be sort of confusing then. It's like, this whole idea of a state is, we can represent a state as like, what space we have left to fill in, and whether we want that space to be filled in with sorry. Oh, sorry, I confuse myself if I do it like the wrong way. So we can say like, dp at n trs is the number of ways to fill in n things such that if one of these things like TRS is like enabled, like it's 1, then we have that in our solution. Does that make sense, Michael? That might seem weird.
That makes sense to me.
Okay.
That makes sense to me.
So it's like I'll do like one quick example. So like if I had like dp of like, what is this, 5 1. So here, this is a good one. dp of 5 1
At the end. So at the end, would you just return dp at n1111?
Yeah, exactly. So yeah, so at the end of the day, we're gonna call like we'll implement this dp thing with a recursive function, and with like a big array to store our answers, and we'll do some at the end. We'll make a function call like I'll do f again because I like f. I'll do like f of like n like 111, where n's like our big overall n. So maybe I should draw it like this, with big N. So the idea is I want to know the number of ways to fill in n spots such that I have a tab. I'm just doing check marks. I don't know why. I have a return and I have a space.
Okay.
Yeah. So yeah, I'm gonna go through like 2 or 3 states just to like make sure it makes sense too. So here, this one's gonna be I'll quiz you, Michael. So here's one possible state where I have like n equals 5, t equals 1, and both r and s 0. So what would the dp value be for this state, Michael, do you think? Like, how many ways could we fill out our thing in such that we have 5 things, and we have tab, and we don't have anything else?
1, just because you only have tabs, right?
Exactly, yeah. So this would be like 5 tab characters. That's what this would represent. Another big insight, let's say I've got like, I'll do 5 again even, and I have 0, 0, 0. How many ways are there to do this?
0.
Exactly. So if I don't use tabs, returns, or spaces, there's no way I can fill in anything that's more than 1. So now we're getting somewhere. I think we could actually even start coding now. I think this makes like some sense. Just stop us if it stops making sense, or if it never made sense. Okay. So let's go down to the code. So I'm gonna do this one in C++. So I don't know. It may be possible to do in Python. I've not seen anyone get full points on this in Python. So I guess generally in competitive programming, you sometimes have to watch out. Like, you can get burnt for using Python. Like, even if you have the right approach, like the constant overhead sometimes a bit too large. Although I will say, if you really want to use Python, you should just try running your code in Python and in PyPy, since PyPy normally. So sorry, here's the trade-off. HackerRank supports both Python and PyPy, and PyPy runs like 10 to 100 times faster. However, Python gets about 10 times more time to execute on the HackerRank platform specifically. So you normally should try running your code with both and see if you can get it to pass. Now, if you're not on HackerRank and you're on a different judge, always just use PyPy. It's just better. It's faster.
Why? I think you're still on on your stream or my stream right now.
I forgot to turn your thing down. I don't think it matters too much. I'm just like, yeah, I was just showing this. Yeah, sorry. So I was showing here like HackerRank supports PyPy and Python. Definitely try them both. Sometimes, back in the olden days when I did a lot of HackerRank, I'd submit with all 4 of the Pythons to see if any of them would pass. You probably don't want to do that, but it's just kind of funny. Okay, so I'm doing C++. Cool. So I guess the first thing I want is a recursive solution. So I want to know. I'll call my function f because I'm not very creative, and it'll take in 4 variables, which are those 4 like state variables we discussed. So it'll be n, which is the number of things. And then, so what is it, 3 n, so do we have tab? Do we have return?
Space.
Do we have space? Now really, I could equivalently do bool, but honestly, so in C++, a bool would just be stored as an int, like most of the time, and you can just use it directly, but you may as well just use ints, like there's not a big difference. Okay. So cool. All right, and then of course we should actually look at the input too. That's pretty important. So it looks like we get this integer n. Cool. So and let me just use that. So let's go In C++, we have to define a variable first, and use cn to read into it. And then, as we mentioned, we're just going to make one function call to like our top level thing. That's all we have to do. So it's going to be n111. So I want to know what are the number of ways to fill in n things where I have tabs, I have spaces. Sorry, I have tabs, I have returns, and I have spaces. Gotta make sure I say that in the right order. Cool. So now we have a lot of cases to deal with, I guess. So first, one case we should probably deal with is, so if n is 0, how many ways are there to make that, I guess? Like, how do we compute that? Any ideas, Michael?
It's 0 because nothing can fit, right?
So I thought it would.
Or is it 1?
It's often 1, right? Like if I have.
Yeah.
I think specifically it's only 1 if t, r, and s are also all 0.
Yeah.
So I'm gonna cheat a bit. I'll just go. So consider if we do t or r or s. This is a bitwise order. I could add them too. It would also work, but. So if I take these values, okay, I want to do this. So if any of these values are set, then I'll take the not of that and I'll return 0. So if I'm trying to make 0 things, but I somehow have to set something, that's not possible. So I return an answer of 0. Is what this boils down to. But if all of these are 0, so if I want to make n equals 0 things, and I'm not going to use any tabs, returns, or spaces, we can do that one way. Which makes sense, I think.
Yes, that makes sense.
Cool. And then I'm going to make this a one-liner, because that's fun. Okay. So now the next kind of interesting insight, I guess, is... So consider our current state, right? In our current state, we have this tab variable, this return variable, and a space variable. So let's think about what happens if t is 0. So if t is 0, that means I'm not allowed to use tabs. Right?
T is, yeah.
Like, imagine, like, if t was 0, r is 0, and s is 0, then there's no way I can do anything, I guess, right? Like, I can't use tabs, I can't use returns, and I can't use spaces. So my answer would just be 0. So I guess then I'll default my answer to 0. And then I'll have cases for if these things aren't 0. So it'll go like, if t isn't equal to 0. Now, in C++, I can just write if t, and we'll do the same thing. And now, we can go and say, well, what am I going to do? I'm probably going to add, like, I want to add on all the cases where I have a tab. And now we can think back to the Jamboard. So we said that the number of ways to place something with a tab was like f at n minus 1. So if I have something of size n and I place a tab, I've got n minus 1 spaces left to fill. But now the question is, what do I use for a t, r, and s? So I guess r and s, I didn't place any returns and I didn't replace any spaces. So if I needed a return or space to start, then I guess I still needed, like, sorry, I shouldn't say needed. It's say, if I'm allowed to use them to start, then I'm also allowed to use them in, like, the next thing, I should say. But what do we put for this t value here? This is honestly the hard insight. It took me a second when I was upsolving this to prep for this, even. I was like, what is this?
You can't just put t?
So, let's think about that. So if I just put t here, and so we know t is 1 right now, right? So putting t here would be equivalent to just putting 1 here. So that would mean that would mean the number of ways I can have a solution where I place a tab first. I would add on all the cases where I fill in n minus 1 spaces also with a tab, like where I already have used a tab there. But isn't there also a case where, like, I use a tab here, but I don't use a tab in my n minus 1 solution?
Oh, yes. Yeah, that's true.
Yeah, so it actually becomes plus f and n minus 1, 0 rs. So to reiterate, this is the same as saying, so the number of ways to fill in n spaces using a tab is going to be the ways to fill in n minus 1 spaces using tabs, and the number of ways to fill in n minus 1 spaces not using tabs. And now...
So is that that argument? Is that like whether or not you can add a tab?
Yeah, I guess so, right? Because it's saying, so this defines a state, right? So this is saying we're in the state NTRS, and this T means that in our state we've used a T somewhere. Anyway.
Okay.
So if we've used a T somewhere, then it means we're allowed to use a T. Because it's like saying what is like the number of solutions where you use a T. Sorry, where you use the tab is what it's saying, right? So I guess yeah, I think that's it. Okay, wait a second. So then this problem is kind of symmetric. So we can do like almost the exact same code for R and for S. So I just have to shift some things over. Now these will be T's, and this will be what, 1, 0. No, this will be.
Have you looked at a Mikhail's solution yet for this
No,
one?
is it clean?
Wait, sorry, what?
Oh, is it clean? I haven't seen it.
I'll tell you after. I don't want to spoil anything.
For context, Mikhail's one of the problem authors for this year. I guess it's Daniel and Mikhail are writing the questions. They're both graduated now, so they don't have like conflict of interest. Okay, so I guess we add these up, and then we return our result, and I think that would give us a correct answer, or what did I guess? Oh, sorry. Oh, there's so many things wrong with this. So first off, so notice our tabs are of size 1, but our returns are of size 2. So this has to be n-2, and spaces are of size 3, so this has to be n-3. Now, do you see any other like really immediate issues aside from the fact that this is like exponential runtime right now?
No, I'm blind. I can't see anything.
Okay, wait. It's pretend your n was like 1 or something.
Yeah.
If I give you n equals 1 and then you go down to like these statements.
Oh, it'll go into negatives.
Yeah. So we need like a case here for, so there's no way to make to fill in like a negative number of spots. So if n is less than 0, you can just return 0. I only know that because I hit that bug also when I was solving this. Okay, so yeah. So this would give us a correct answer then, but it would be super slow. And it's super slow, and you'll notice we're also supposed to print our answer mod 10 to the 9 plus 7, and I'm not doing that. But it should pass the small test cases, so let's try running it. So if we run this, cross our fingers. Yeah, cool, so we passed the 2 small test cases, and then we fail this test case because we time out, and we don't take the mod, so we can fail it twice over. So the first easiest change is to take the mod. So they say, you'll see this a lot in competitive programming problems. They'll say, like, print your answer modulo 10 to the 9 plus 7. The reason they do this is that your answer starts to get pretty large. And so in C++, like, integers are finite. They can only store integers that are so big. Like, I think it's, what is it, like 2 to the 64? Oh, I'm going to get this wrong. It'll be super embarrassing. It's like 2 to the 64 minus 1 if it's unsigned. If it's signed, slightly less. Yeah. Anyways. Sorry, got sidetracked. But so they're limited, right? So you have to worry about overflow and things. So what's standard is that... Oh, sorry, I should clarify. It's 2 to the 64 minus 1 if it's an unsigned long. It's only 32 bits if you're using a regular C++ in. Yeah. But so, to avoid overflow and things, they make it so you apply like a mod operator after all your operations. And that just like keeps it within like a fixed like range of values. So what we're going to do is we're going to say...
Does that slow it down in any way?
Mod? I mean... You have to pay for the mod.
Adding extra mod, oh right.
But it's like it's not really any more expensive than like maybe like a division or multiplication. It's pretty cheap.
Mm.
So you have to put 10 to the 9 plus 7 here. So let's go there.
Oh, I can hear the keyboard.
Yeah.
We should have for the contest. We should just have
an audio
like
stream
a chat or something. Yeah, a live stream of your keyboard. You should run keyboard view.
Keyboard cam. I've seen people do. I think literally like Airchico or something. Like the competitive programmer does that.
Mm-hmm. Face cam and keyboard cam.
Yeah, literally that. Okay, sorry. So what do I want to do here? Oh yeah. So I have to change this to mods. It's gonna be like I want to go res. It's kind of annoying. So I do this. Okay, mod. So there's another really annoying thing. So if I add 3 things, it's actually possible that it will overflow. So you either have to use like longs instead of int, or you have to do this. So I'm just going to do this. So yeah.
You're not going to do int long?
No.
What's you do again? Define int long?
That's my word crime. Yeah, I love that. Sometimes I get burned for it, and like people have like no sympathy for me if I get burned on it. It's fair.
Wait, does it actually break your code sometimes during int long long?
No, not often. It's normally fine. It's pretty hard. I think it almost always it just makes it safer, right? Because there's nothing worse than like when it overflows and you don't notice, and then you cry.
Yeah.
I think that you can turn on. There's a thing for C++ called ubsam, like undefined behavior checker, and it will tell you like whenever you like overflow, so you don't have to like it doesn't happen silently in the background, which is super nice. You can also like you can enable checks in your compiler to have it check for things like out of bounds memory access, and like out of bounds vector access. So that saves me like so much time on debugging. Actually, I'll even like, I'm not, this.
Oh, when you run it offline, right? When you run it.
Yeah.
Because you normally type your code
so
in your own.
I should say that too. Normally, if you do more competitive programming, like on HackerRank, you have this editor here. Most sites don't have an editor like this. And plus, you'll find, I don't know, if you have more of a setup, you might find it more convenient to type on your own machine.
Mm-hmm.
So I guess I normally type on my PC, and I've got like this giant gnarly template I use. Like that's what Lucas is talking about. I've got like this nasty like define int long macro in there, and like a bunch of other stuff. You know what? For the sake of the stream, I'll even show this disgusting mess.
Lucas asked for the macros too.
Lucas wants to. Lucas, this is just for you.
Define int long. Define int long.
Okay, I need. Where is my terminal? This way. This guy. Okay. So you should see my lovely Windows terminal. No, that is not my Windows terminal. Wait, what is this even?
Oh gosh.
Looks awful. Wait.
What is that?
I honestly don't know. Oh wait, is this like an OBS pop-up?
It's your OBS and your OBS.
Am I showing my OBS on my OBS? Okay, let me do this better. Okay, wait. Let's try again. It says Windows Terminal. What is this? It's a prank.
Oh, maybe it's just maybe share your entire screen.
Yeah, I'm just gonna share my screen.
Is that too much?
No, that's fine. You guys are getting the full stream view just for this stream. Okay, let me do here.
Behind the scenes.
Behind the scenes, yeah. You can see the chat, all the fun stuff. Okay, display capture. Let's go. Awesome. Okay, so you guys should see
my gosh.
Lots of recursion.
Yes.
Alright, Michael, does it look good? Actually, I can't even see it.
That looks fine. That looks fine.
Okay, awesome. So I'm gonna quickly show.
It's kind of cut off a bit. It's more to the top left. You gotta.
Oh gosh, do here? Is this better?
Drag it over. Yeah.
Oh,
that
I see.
looks fine. Yeah.
Okay, this is good.
There you go. That's
so
perfect.
See my beautiful terminal. Okay. So I also. This is so funny. So I have this templates thing. It's not even a real file. It's actually a symlink. I symlink my templates to like this secret directory, and then I have this directory hosted on GitHub with all my templates. But that's an aside. So this is my baby template. I do this when I want something like really light, and then when I don't want something light, I've got my heavy template. And my heavy template.
Oh my gosh!
It's just like 300 lines of C++. And the cornerstone of my template is define int long, which it makes all my ints long, so it means all my integers will have 64 bytes instead of 32 bytes, which prevents overflow. And the other thing I do, which is super useful, so I've got macros for compiling things, and my favorite macro is this. I can press F in my terminal and it compiles, and you see I've got all these like really like wonky looking flags here. So these flags will tell me if I access memory out of bounds, or access vector out of bounds, or I do other sketchy stuff. It's beautiful.
Wow, that's useful.
I can also like I can go to directory. Oh wait, and I can go like what? Oh, let me just rm.rf this whole directory. Oh wait, what's my thing? It's like yeah. So before a contest, I do 10con, and it dumps like all the files for me to write a contest.
Oh wow, A B C D. You got all the folders there too.
Yeah. It looks gross because there's already files here, but it's cool. Okay. So let's get out of that. Let's go back to the real thing. Actually implement this guy. Okay. Okay, so we did our mod. We did our mod there. We actually did mod twice, so it went overflow. That's good. So this is still super slow. If we run this, we're still going to time out, which stinks. You'll see, ran out of time. Very sad. So here's the trick. Here's why like DP is amazing. So what would happen if we made an array, which we call, or I guess like a 4-dimensional array, which sounds fancy, but it's just like an array with 4 indices. And in this array, I stored like all our possible states. So what would that look like? That would look like Here, this is a little thing I do. I'll go like, is this 10 to the 5? Yeah, so I just want to figure out what the maximum size is for this thing, and I'll allocate an array of that size. So this can be at most 10 to the 5, so I'll make this like what? Like 10 to the 5, like, 1, 2, 3, wait, one more. And I'll make it like +2 or something for peace of mind. Okay. I'll make it +3. I don't trust myself. Okay. Okay. So I allocate a big array here. And then the idea is, whenever I compute a solution, I'm going to store my solution in that array. And whenever I go to like compute it, like whenever I'm like here basically, I'm going to check and see if I've already computed something and use it if I've already computed it. So then the big brain thing there is, if anytime I compute something, I store it in my DP, and anytime I want to compute something, I look it up. That means the total amount of work I'll do will be equal to the total amount of work to compute all the states. And we see that to compute one of our states, it's just constant work plus whatever the cost of the recursion calls is. So that means then my total runtime is going to be proportional to just like the total amount of memory I allocate for all my states. So here, I allocate 10 to the 5 memory times 8. Like 10 to the 5 times 8, like integers. And so 10 to the 5 times 8, that's like, I guess nearly 10 to the 6. That's a totally okay amount of memory to allocate. So we know we'll have like good runtime.
What's a not okay amount
of
memory?
It starts to get shaky. 10 to the 7 is still like pretty okay. 10 to the 8 gets shaky, and it gets kind of weird. 10 to the 9 is like you're done for sure. You can't do it.
Okay.
Yeah. Okay, yeah. So let's just do that. So, let's do the here first. So first I'll do if dp, this is the tedious part, at n, at t, at r, at s, isn't equal to, I'll initialize it's like -1. So by default, because it's up here, it would be initialized to 0. But the trouble is some of our answers actually will be 0. So we have to make it something that's not 0. So I'll arbitrarily choose -1 as my like default value. So I'll say like if it's not the default value, that means I've computed it, and that means I can just return it. Otherwise, I need to compute it, and once I'm done computing it, I'll store my computation. So like I'll store the value in the DP. And then I need to do this other annoying thing. I need to go, and I need to initialize all the memory to -1. Now I always want to use memset here, but I'm pretty sure like memset doesn't actually work all the time when you do this here. It's actually scary. Be very careful.
So why do you use just normal arrays over vectors?
Oh, there's actually no reason. I've mostly switched to using vectors now. It's mostly a force of habit from declaring big global arrays. It's honestly the biggest reason is that if I don't do this, like let's say I do use vectors, then I have to type vector, a vector, a vector, a vector 4 times, and it makes me really
this happens kind of.
It's just gross. Another alternative way you can do this is instead of doing like a 4-dimensional thing, you could just do like int dp n of 8 and make it treat this like a bit mask with three binary digits.
Yeah.
But that's like the same idea. Yeah. Lucas says memset caused him to wrong answer in the competition. So be careful of memset, kid. It's scary.
Oh no.
So instead of memset, I'm gonna do this I'm gonna do a bunch of for loops. Get ready. Also note that you don't need curly braces for your for loops. They're overrated. Okay, let's go here. Copy and paste this 3 times. Beautiful. So I'm just iterating through all possible values of every state. I'm going to set for each one, let's go dp at, I said I, sure, dp at I, at t,
Jesus.
at r, s, equals -1. Here, this is something fun too I like to do. Most people think this is gross, but I actually love this. You go like this. Today on More Crimes Against C++.
Oh god. Why do you like that, Wyatt?
It's so clean. It's all in a row, you know?
Yeah.
Yeah, see? Yeah, this looks nice. So cool, so we've initialized all our memory to 0. We make our recursive call. We remembered to take all our mods. We handled our base cases. We do our computation. We store our answers and we look them up. So this looks pretty good. I'm actually pretty confident in this. What's your over-under, Michael?
I believe.
You believe? That's all right.
I believe it's gonna work.
I believe.
Yeah.
I believe. Let's see.
Crash.
Why? Okay, so the problem here
Define.
is I made this n, and then I also made this n. So let's just make this lowercase n. So you see, I use this macro here. Macros are people kind of hate on macros, and it's kind of justified most of the time, honestly. Because like what the compiler did there is it replaced my n here with this number here, so it was like int. It did this. I guess the precompiler I should say, or sorry, the preprocessor turned my code into this, which is gibberish. Makes no sense. So be careful of macros. So let's try again. Cool. So we passed the samples. Let's submit this bad boy. Cool, and we pass all the tests. So if you can do that at comp, you can beat like literally everyone. So if you can understand like the DP, you got this.
That's not bad.
Yeah.
Okay, so Mikhail's solution.
Oh yeah.
Let's see.
Share it? I can share your screen.
He did. So he treated this like a coin change.
Oh yeah, that makes sense actually. That does make sense.
Yeah, and he also did that bitmask thing you were talking about, where he made it a 2D vector, and he did 8. He did 8 as his mask.
Mm-hmm. Yeah, that makes sense.
And you can see like where he does auto DP, he grabs that bit. Wait, is that how he does it?
Auto DP. Yeah.
Is that right? Oh yeah, that's right. That's right. Yeah, he grabs the bit there. He does. And he kind of has the same thing as you.
He does a reference.
But he doesn't.
Yeah, he does a reference there, so we can modify it directly without writing that whole thing out every time.
Yeah, and he has the same like state thing as you here.
Yeah.
He does it.
He does it.
So why? Oh, sorry. Go ahead. Why?
Oh, sorry. I was gonna say. So I did mine like top down with recursion. The way Mikhail did it better here is actually way better. He did a bottom up with like for loops. So if you do that, you don't have to pay any of the overhead of the function calls. So it's like much faster. So sometimes you have to do it this way to get it to pass.
Mm-hmm. Yeah, this way looks really nice.
Yeah.
Yeah, you see a lot of your stuff.
Look at his built-in pop count. Look at that. That's like a compiler built-in. That's like it counts the number of bits set. It's a sneaky thing.
Wow.
Yeah.
All right. That was good.
I think that's all. Unless people have questions in the chat, that'll probably bring us to close to the end of the stream, I guess.
Yeah. What? Let's do last 10 minutes. Let's try to do the infection together.
All right, I'll pass that one to you, Mike.
Who wrote this one?
Daniel, I think. I just know I didn't. I made one like cheese solution for Daniel. Actually, look, I'm not even in the top like 5 for this. Look at this.
Really?
Scroll. Oh my god, I'm not even in the top anything for this.
I remember a lot of people really like this problem. Like afterwards, they're like talking about the infection a lot. Like they're like, I was really close to solving it.
Yeah, I got 1.5 points. I wrote a pure brute force, and then I commented in my code like, "Hey Daniel, hope you like reading this code."
Yeah. So the secret is focus on the easy ones to maximize your points, because as you can see, Wyatt got the most points.
And spent no time on infection.
Oh man, I might participate this year. This was kind of fun.
Yeah, it's pretty fun.
This one wasn't bad. I'm surprised not that many people got it.
Yeah, actually, no, yeah.
And Lucas failed because
I feel like it's not crazy. I feel like people aren't very familiar with dynamic programming in general. I feel like it's a big thing.
All right.
I believe.
Any last questions?
Oh wait,
I'm doing infection.
Yeah, go for it. We can figure it out.
Okay.
Wait, how much time do we have? We're also, I think Michael and I are like triple booked today, so we don't have like a ton of time, but.
Yes, I have a lot of things to do today. All right, I'm doing it. I'm submitting my code.
I believe in you, Michael.
This is what I'm gonna get. It's processing. Let me zoom out a bit.
Oh, actually, no, fine, yeah.
Oh, yeah, 0. Let me debug this. I'm gonna change this to a 1. Put it again.
Did you really do that? Do you get many points?
Oh yes, 1.54. No. I got 1 point.
That's the same score I got doing like a full brute force. That's so disheartening. I had to write like 60 lines of code to get that much. Disappointing.
Damn. Taking me, everyone above you, Wyatt. All they did was print 1. Maybe these guys print 2. You want to see what Toby did?
Yeah.
Maybe Toby did print 2.
Public Toby roast.
Oh wait, is there a way for me to see?
Do you view all submissions?
Oh, can I see it like in here?
Yeah,
can
no,
I be
no,
like?
You have to go to the general thing. Like go up to MCP tryouts. Now click view all submissions.
View all submissions. Oh, to find it?
You can just search for Toby. Or we can't search, but once you
Is there
find
a
Toby.
search bar?
No, you have to find Toby, sorry.
Alright, let's see
I
my
like
short.
it.
Let's see my short. I swear the leaderboard had a thing that let you see. Okay,
Yeah.
that's all.
Oh, that's not
This is, I really should have done
we're
that.
doing the 1.54. I mean, that's fine. We only have like a few minutes left. If you guys have any questions, though, throw them our way. Or about like tryouts
We'll
or
hear.
getting better, or getting ready, or anything. Or what we're covering on the Thursday workshop. I'm pretty excited for Shaz this year. They're bringing in so it's Mikhail and Daniel reading the questions. They're bringing in like Shamu as like an external like tester, just like validate.
Oh, that's fun.
Yeah.
That's fun. Is it cheating to watch the live stream while you're doing it? They're not gonna say anything revealing, right?
No,
During the live
they'll
stream.
say general stuff. I don't know if they'll keep talking the whole time. They may just do like music or something. We'll see if they. They're definitely though. If you stick around, like once the contest finishes, they're gonna do like we'll do the announcements for like I guess all the winners and everything. But then also like they're gonna go through the questions, which is like the I guess the most enjoyable part, I guess, because they talk through all the problems and how to solve them.
Fun.
From the authors themselves. Ooh. So we have a question in the chat from Osama Saudi, and I'm sorry if I absolutely butchered your name. I saw some stuff on advanced techniques. How handy are those for ICPC or even tryouts? Ooh, so I guess that just going off last year and like previous years, I feel like you don't need many advanced techniques. Oh, on the Notion? Oh, so let's actually pull that up for context. Let's get full context here. So that's actually pretty specific.
It's on my screen right now, by the way.
Oh, really? Too bad.
Yeah.
I'm also pulling it up. Okay. Wait.
Oh, no, I meant your stream.
Oh, really?
So,
Oh, that's awkward. True.
yeah.
So, actually, thank you. I'm sorry. Sorry for trying to roast you unsuccessfully.
That's why.
Okay, let me go. Remove book. Okay. Awesome. So I guess, yeah, for anyone who didn't see it, we posted a Notion a while back where we posted like a ton of techniques. And they start off like pretty easy and get like much harder. So I guess if by the advanced techniques you're referring to like the level 3 techniques, these are like these you might see. Actually, I can go through like very specifically what you'd see. So at ICPC tryouts, you have the potential to see Fenwick trees, segment trees, advanced graph theory, maybe binary lifting, but I doubt it. You could see game theory, you could see flow, and you'll see a ton of geometry every year. They always have like 2 geometry questions. So at ICPC, these are like pretty useful to know. But at tryouts, I don't think you'd see anything here, except maybe game theory, just because one of the guys loves game theory. But even that, I can't see, honestly. The only things you really need to know are like know your basic data structures that are here, and know how to use like, hey, this is like how I do like a depth first search, breadth first search. This is how I do basic dynamic programming. This is how I do like a sieve of, or there's a thing called a sieve of Arrhenius to calculate primes. I'd learn that for number theory, and I'd learn maybe the extended Euclidean algorithm. That's probably overkill, honestly. But that's pretty much all you need to know. So for tryouts, like you don't need to know like a ton of stuff. But for ICPC, it's good to know more of this stuff. But if you make it onto a team, we'll like train, I guess, for like the actual regionals are on March 6th, so we have like a little under a month to get ready. So we'd be training there.
Mm-hmm.
Yeah. Well,
so also, like up to DP would be enough, right?
Yeah, up to
for
DP,
the tryouts.
Yeah, up to here, more than enough, easily. Also, if you, I guess I typed most of these up. If you guys see any mistakes in these, or like if they literally don't make sense, please like message me because I will update those. Yeah, I guess it only gets better with like feedback. I still like these photos. I wanted to do Michael, originally for this like level 3 thing, I wanted to do like the, like the Doge meme where there's like the really like muscly Doge, and there's like the small Doge.
Yeah, I know that one.
I was gonna make
that.
It was gonna be really cringe. I didn't do it though. I wanted to. Oh, going through cracking.
You gotta put that on the live stream next time.
Yeah, the Doge.
We do the guy who's doing the question has the muscle Doge, and the guy who's listening has the sad Doge.
I liked her, Cedric.
Yeah, Cedric was good.
There's honestly so many things. You put Cedric, you put the Doges, you could use that CLRS. CLRS is like the famous, it's like the meme algorithm textbook, basically. Alright, so one more question from Osama Sadi. He says, damn, going through cracking the coding interview, should I jump right into Code Forces after that, or read up on other competitive programming books? honestly, with competitive programming, nothing beats like hands-on experience. Like it's like a really uphill learning curve at first, but I think like if you just like read the like the, I know there's two things. For one, if you just like read through the like the theory, it's gonna get boring at some point, and two, like if you never apply it, it's hard to have it like actually stick in your head. Yeah. Plus, like normally like on HackerRank, it used to be that you could like basically just like cookie cutter like put in an algorithm like line for line almost, and that's all you needed to pass the question. But on sites like Codeforces and at ICPC, you normally need to. There's more subtlety. It's like you don't need to understand the algorithm. You need to understand like the sort of logic that would like bring that algorithm into existence, like the similar logic, like a similar style of thinking, or maybe you have to use the algorithm as like a sub-step or something. So I don't think anything really can compete. Sorry, compete's a bad word. Can like compare with actually just writing contests. Like you should really do. Like if I was starting out, like if I was in first year or second year right now, or even third year, and I hadn't done like as much competitive programming, I would go onto Codeforces. I would go to this contest tab. I'd make an account if I didn't have one, and I would find educational Div 2s, regular Div 2s, and in particular Div 3s. And I would try and write like most of the Div 3s, like see how much of a Div 3 I can get through, and maybe do like the first or second question, maybe even the third question in Div 2s. And that'd be really hard to start, but that would get you like really good, really fast, I think. And also, shilling it out, I would go to, I have to log in? Wait, here, flex my Codeforces. Okay, you should, okay, you should watch, I went here and then I went all the way down here. You should go to McMaster University and sign up here. Because nobody, people make Codeforces accounts, nobody signs up to the Codeforces McMaster group. It's a ghost town in here, so you gotta come in here.
Every stream, you gotta see why it's purple color until it goes away.
Yes,
until it goes red.
Until it goes red. Oh, I'd be happy. I think I'm gonna go back down to blue. We'll see. But I've been doing well recently.
Oh, do you get stressed? It's like so high that it could drop at any point.
Honestly,
I feel like
I'm a little stressed. I have a Smurf.
When I play like chess, right, it only goes down like 5 points, 6 points, right?
Yeah.
But on Codeforces, it can go down like 200 points on a bad day.
But it can go up 200 points. That's
way.
Right? You got that.
It could go up 200.
Oh, I got another really good question. Does higher div equal easier? Yeah, exactly that. So div 3 is the easiest. Div 2 is a little easier. So actually, I could tell you. So div 3, like for me, I can write like a whole div 3. I feel like you're gonna expect to solve probably 3 or 4 questions. Maybe I don't know. Maybe 2 or 3 questions. Maybe actually no. I should need 2 to 4. Let's say I'm pulling these numbers fully out of my ass, but 2 to 4 questions if you're just starting Codeforces and div 3. I'd say maybe if you have some programming experience. Totally random numbers, but like I can like full solve a div 3, and I solve like what 3 to 4, maybe 5 on a really incredible. No, I don't think I've even done that. 3 to 4 questions on a Codeforces div 2. Typically. Oh, the other huge thing about Codeforces, which makes it so good, is so Codeforces, you do the contest, right? And then you're all done, and then you go, well, I made it this far, but I didn't get the next question, right? So let's say I didn't get this question. Well, I can click on it, I can try it, and if I still can't get it, I can go down and they'll have a tutorial that explains like in depth, like they'll give you like a hint, or they'll say like, hey, here's a big explanation of how this works, and they'll give you like code, like here's the code. Oh, go here. Here's the actual solution code that implements it. So you can like actually like figure it out and get better. So the idea is, I guess, you upsolve, they call it, which is like solve questions after the contest, and that's really how you improve. I think one of my friends told me like if you just write contests, you're really just like measuring up like where you are, versus if you actually upsolve, that's how you get better. At least hopefully. The other funny thing is div 1s are like stupidly hard. They're stupidly, insanely hard, to the extent that I'm purple now. For like after not being purple for a long time, you can only write div 1s if you're purple or higher. So I couldn't even write div 1 most of the time. Like I'm not even allowed. I'm too low to even write them most of the time. That's how hard div 1s are. So don't be demotivated if these are challenging to start.
I think we got signed off. We got another meeting to head to.
Yeah. Oh, did our other thing get pushed?
Yeah, it's starting right now.
Oh, okay. Okay, thank you everybody for coming out to the live stream. Make sure to tune in on Thursday if you want to go over some algorithms. We'll go through, I guess, some of those things you saw in the Notion. And peace out.
Bye, guys.